Welcome! Today, we're diving into some real-world problems that show just how powerful Excel can be for engineering economic analysis. We'll tackle 3 different scenarios: deciding between contractors for a sprinkler system, measuring how postage costs have grown over the last century, and figuring out equal loan payments. By the end of this video, you'll not only know how to solve these problems, but you'll also see how Excel makes the math easier, faster, and crystal clear. Let's jump right in. Bill wants to install an automatic sprinkler system at his cabin. The lowest professional bid is $5,500 from Sprinkler Works. Bill initially tries to do it himself, spending $1,100 total on materials and $160 a day renting the required equipment. He keeps all rentals for 5 days before giving up and decides to hire a contractor to finish the work. At this point, Sprinkler Works says they can finish the job for $4,500, since they can reuse some materials and trenching. Meanwhile, another contractor, Water Systems, offers to finish the project for $6,000 with brand new, top-of-the-line materials. Based on this scenario, how much has Bill already spent? How much will they have spent when the project is over if they accept the new offer from Sprinkler Works? Should Bill go with Sprinkler Works or Water Systems? Why? Of the 10 principles of engineering economic analysis, which one is, or which ones are, well illustrated by this problem? Of the systematic economic analysis technique's 7 steps, which one is, or which ones are, well illustrated by this problem? To answer these questions, let's first insert and label the provided variables in separate cells. This includes the 5 days that Bill rented equipment for, the total cost of materials, and the daily cost of renting all the equipment. We can find how much Bill has spent by adding all cost Bill incurred during the 5 days he tackled the project himself. To do this in Excel, we will type in the following formula: equals C4 plus C5 times C1. This multiplies the rental rate by the 5 days and adds them with the total material cost, resulting in $1,900. This is how much Bill has already spent and represents his sunk cost, the money he'll never get back. To figure out how much Bill will have spent if he accepts Sprinkler Works' offer, we add the $1,900 sunk cost to the quoted cost of $4,500 to get a total of $6,400. Notice something important here. On the surface, Sprinkler Works comes to $6,400, and Water Systems comes to $7,900, which we get by adding $1,900 to Water Systems' offer of $6,000. But the $1,900 Bill has already spent is gone no matter what. It's a sunk cost. What really matters are the future costs: $4,500 to finish with Sprinkler Works and $6,000 to finish with Water Systems. Since $4,500 is less, the smart choice is to stick with Sprinkler Works. This problem illustrates 2 key principles of engineering economic analysis. Principle number 2: always compare the relevant future costs between alternatives. And principle number 10: ignore sunk cost. It also highlights the importance of systematic analysis steps. Number 1, identifying alternatives. Number 4, estimate the cash flows. Number 5, compare the alternatives. And number 7, select the preferred investment. The takeaway? Sunk costs don't matter, and since Sprinkler Works' future cost is lower, Bill's best move is to go with them. Our next problem looks at how compound growth works. On July 14, 1919, first-class postage for a 1-ounce envelope was 2 cents. By July 14, 2025, a first-class stamp for the same envelope cost 78 cents. What annual compound increase in the cost of postage occurred over this 106-year period? Because this problem deals with compound growth over time, we use the standard compound interest formula. F equals P times 1 plus I to the power of n. Here, F is the future value, P is the present value, n is the number of periods, and I is the annual growth rate we're trying to find. Rearranging the formula to solve for I, we get I equals F over P to the power of 1 over n minus 1. In Excel, we enter the formula as followed. equals b2 divided by b1 to the power of 1 over b3 minus 1. The result is 0.035166. To display this as a percentage, right-click the cell, select Format Cells, choose Percentage, and set it to 2 decimal places. This gives us 3.52%, meaning the price of a first-class stamp increased by about 3.52% per year, compounded annually, over 106 years. Another way to solve this in Excel without rearranging the math yourself is to use the built-in rate function, which is designed for problems like this. In a new cell, type equals rate, open parenthesis, B3, 0, -B1, B2, close parenthesis. Here, B3 is the number of years, 0 is the annual payment since there isn't one, -B1 is the starting value, and B2 is the ending value. Format that result as a percentage, and you'll see the same 3.52% growth rate. Our last problem is all about loan repayment with equal payments over time. A debt of $1,000 is taken on at time 0. Drake wants to pay it back in 4 equal payments at times 1, 2, 3, and 4. The interest rate is 10% per period, compounded each period. What will the size of each payment be? This is a classic present worth of an annuity problem. The present value, PV, of an annuity is the current worth of a series of equal future payments, discounted back to the present day using an interest rate. We use the following formula to find this type of present worth. Here, P is the present value of the loan, A is the uniform payment we're solving for, I is the interest rate, and N is the number of periods. Since we want to isolate A, we will rearrange the formula as shown below. That's the math, but Excel makes this even easier with the built-in PMT function, which is specifically designed to calculate equal payments on loans. To use this function, we type in the required variables into Excel. Next, we will type in the following formula in an empty cell. Equals PMT open parenthesis B2, B3, -B1 close parenthesis. Notice the negative sign on B1. Excel uses cash flow signs, so the loan, an inflow of $1,000, is negative when we're calculating payments, outflows. Hit Enter and Excel gives $315.47. That means Bill will need to make 4 equal payments of $315.47 at the end of each period to completely repay the $1,000 debt with 10% interest. This problem nicely illustrates how annuities work and how Excel's financial functions save you time on repetitive calculations. And that's it. 3 very different problems, all solved using the same approach. Break down the numbers, use the right formula, and let Excel handle the heavy lifting. Whether it's ignoring sunk costs, calculating compound growth, or figuring out equal loan payments, the principles stay the same. If you found this helpful, make sure to like and subscribe. In the next video, we'll keep building on these skills with more examples of time value of money and decision-making in engineering economics. See you then.